Hi everyone, today I'd like to start by introducing a concept that bridges physics and mathematics, Newton's law of cooling. This principle, developed by Sir Isaac Newton in the 18th century, describes how an object's temperature changes when it's exposed to cooler environment. The idea is simple yet profound. The rate at which an object loses heat is directly proportional to the difference in temperature between the object and its surrounding. This relationship not only highlights Newton's brilliance, but also plays a significant role in fields like engineering, meteorology, and even forensic science. Over the next few minutes, we'll explore this law, how it works, and its real-world application.
The problem is to investigate how an object cools in an environment with a constant ambient temperature. There are numerous studies have applied Newton's law of cooling, such as thermodynamics, in everyday life. Overall, Newton's law of cooling holds significant relevance in engineering, physics, and everyday application, providing vital insight into thermodynamics and heat transfer phenomena. We use Mathematica because we find the intuitive interface to be extremely useful for both learning and project work. The layout is simple, allowing us to easily navigate through the various functions and features without feeling overwhelmed. This user-friendly environment enables us to concentrate on understanding the concept underlying our project rather than getting bogged down in the technical detail.
So for our numerical solution, this differential equation is dt over dt equal to negative k t minus t mv, which is the t uppercase is temperature, t lowercase is time, and k is constant temperature, and t mv is ambient temperature. And our Euler's formula is T n plus 1 equal to T n plus h times with dt over dt, d temperature over d time. So we substitute all the value and we repeat this process for every time step, which is h equal to 1 until time equal to 100. So the temperature gradually approaches the ambient temperature, which is T ambient equal to 35 degrees Celsius over time.
So now we go to the coding section. We use Euler's method because it is a straightforward numerical technique that helps approximate solution to differential equation. So before we go to the coding, I want to briefly talk about Newton's law of cooling. Newton's law of cooling states that the rate of temperature change of an object is proportional to the temperature difference between the object and its surroundings. So here is the code to implement Euler's method in Mathematica. First thing, we define the parameters such as the ambient temperature, initialize the temperature, cooling constant, step size, and total simulation time. Then we initialize arrays for time steps and temperatures. After that, we use a for loop, iterate over each time step, updating the temperature using Euler's formula. Finally, we plot the result using list line plot to visualize the cooling process. So here is the output from the previous code. As we can see, the plot shows how the temperature of the object decreases over time. Initially, the temperature drops rapidly due to the large difference between the object and the environment. As the temperature approaches the ambient temperature, the rate of cooling slows down. And this behavior is consistent with the exponential nature of Newton's law of cooling.
In conclusion, Newton's law of cooling provides a fundamental understanding of how heat transfers, with the rate being proportional to the temperature difference between an object and its surrounding. By leveraging tools like Mathematica, we can precisely model, solve, and visualize this behavior, allowing for a deeper understanding of real-world thermal systems. This combination of theory and computational power makes it an invaluable tool for analyzing and solving practical problems in science and engineering. That's all. Thank you.